Phones away, Chromebooks closed up, and pay close attention. Because again, some people were kind of disturbed that you were getting a little bit of calculus notation on Friday, but any four-year college now requires you to have 4 years of math. So whether or not you see it this year or you see it next year, you're going to encounter limit notation. So I don't want to teach you up and up, up and down, down and up, and all of that stuff that gets you nothing, so that you can't go anywhere next year if you decide to, because you should take a math class all 4 years while you're here. And in college algebra, your book is not going to say up and up and down, down and up. It's going to do limit notation. So we had started with the up and up yesterday. And one of the things that's really hard to get across to people is that this LIM, that's a part of the notation. You know, we never write out full words in math if we don't have to. And that's a part of the notation. And underneath that is where we put X arrow to mean X approaches negative infinity. And f of x just stands for y. And y is all about up and down. And that's what y is for. So for this one, we're saying as x goes, imagine the number line like I had in my 5th grade math teacher's class. So a 0 right here, the negatives are going that way. So as you go to the left forever, this is asking, is your graph going up or is your graph going down? So if we only look at the left part of this graph, right there, you see the arrow showing us, hey, that's going up. So our job is to put infinity in there, because infinity means it's going up. Negative infinity means it's going down. Now, if this one asks about going to the left, it's just natural that the other one should say, hey, as we go to the right forever. So the limit as x approaches infinity, that means going to the big numbers, the really positive big numbers of our graph. And our job is to determine whether or not we should put infinity or negative infinity. And that's fine. Well, with this first graph, it doesn't matter if you go to the right or you go to the left, you're going up. That's what's happening. So that's going to be infinity. Now that's not the same for the next one. You know, that's why we do this. They are not the exact same for each one of these. For each graph, you have to say, oh, as I go to the left forever, what's my graph doing? As I go to the right forever, what's my graph going to do? So for the next one, and I write too big, so I'm probably going to have to put one up here. Limit as x approaches negative infinity, f of x, my graph is going somewhere, and limit as x approaches infinity of f of x, my graph is going somewhere. So that limit notation is exactly the same every time. The only difference is what do you put after the equals. What you see determines whether or not it's going to be infinity or negative infinity. Is it going down as you go to the left forever, or is it going up as you go to the left forever? Is it going down or up as you go to the right forever? So the top one here says x approaches negative infinity. That's the left. So we look at this graph and we think, okay, I don't need that part, I just need the left. Oh, my arrow's going down. And I fill that little blank in with negative infinity. Then this one is telling me as x goes to infinity. So as I go to the right forever, if I cover this up, now I'm going to the right from 0. And that's going down again. So both of those will be negative infinity. Like I said, in the back of the book, they're going to put down and down. I don't want to see down and down on your papers. I want you to get used to this. Notation is all it is. You know, math is a different language because we try not to write everything out in words if we don't have to. Now, the next one, same thing to start with. Limit as x approaches negative infinity. F of x is doing what? Limit x approaches infinity. F of x is doing what? So we write those same things every time, just every time. And if you search on, it was a little overwhelming, I didn't want you to see it, but I thought I'm just going to Google and see images of limit notation. And you get just pages and pages of what we do with limit notation in mathematics. All right, for this graph, if you start at 0 and you go to the left forever, should we put positive infinity or negative infinity? Is it going up or down on the left-hand side? Down, so negative infinity. How about if you start at 0 and go to the right forever? Where's it going? Up, so positive infinity. There it is. All right, last one. Limit as x approaches negative infinity, f of x equals limit as x approaches infinity, f of x equals. So last graph over here. Left-hand side of that graph, where's it going? Right-hand side of this graph, where is it going? So it's just learning that positive infinity is up and negative infinity is down. That's it. But the notation is the same every single time. So if we get used to that, this is not going to be the toughest thing in the world. And like it says down here, there are some books that use mathematical notation like this to fill it in, but when you get to pre-calc, when you get to college algebra, this is what we're going to want to see. Not up and up, not down and down. So, why teach you that now instead of just waiting for you to see it next year? Because next year, your teacher's going to assume that you already saw it. So, when they put it up there, you don't go, oh my gosh, what is that? And they have to start fresh. So, if we just practice it a little bit, we'll be okay. The end behavior of a polynomial function can be determined from its leading term, a times x sub n, when the polynomial is in standard form. That's why it's so important that we get these in standard form, because then that first term tells us the overall shape of the graph. So end behavior of a polynomial function of degree n with the leading term of a times x sub n, moving away from the origin. Now this is a really nice chart. However, we need the visual because we want to know what the graph is going to do. And I already went over this with you on Friday, but I'm going to remind you of it. And that is, if the degree is even and we have a leading coefficient that's positive, those are always going to look like big parabolas. If you make your window big enough, they're going to look like big parabolas. And then we would say the limit as f of x, as x approaches negative infinity, f of x is going to positive infinity, and the limit as x approaches positive infinity is positive infinity. If our leading coefficient is negative, if we make our window big enough, we'll have an upside down looking parabola. So this one would be negative infinity and negative infinity for our two little slots to fill in. That's not too tough. So what about if it is odd degree? Well, again, it depends on your leading coefficient. Is it positive or is it negative? So if your leading coefficient is positive, it's going to look like a S-curve, a snake-like curve. Want to graph that? And if your leading coefficient is negative, it's going to look like it's been flipped over the y-axis, like it's been reflected over the y-axis. So these, they take a little more thinking. I mean, it's kind of nice with even degrees. They're both always the same. They're either both up or they're both down. But with these, positive leading coefficient, we're going to put negative infinity in that first slot as we go to the left forever. And this one to the right. All right, so to the right would be positive infinity. This one will, to the left, be positive infinity, and to the right be negative infinity. So they're kind of backwards as you go through that. So why is it then that if you put in x to the 6th and it has a ton of x's after it, it doesn't look perfectly like this? Because the other x's that come after it make little lumpy bumps in the middle, and those are called turning points in math. So if there are a lot of terms, they're not going to look perfectly like this, but where these arrows go will be exactly the same, no matter what. And that's the end behavior, and that's what we're talking about right now. So all we need is this little itty bitty sketch, and we'll know what the overall shape of the graph is going to look like. So all even degree functions, those are our parabolas. They behave as parabolics. All odd degree functions behave as S-curves, those snake-like curves. So problem 2 says, we're just going to give you a polynomial. You tell us, what is this going to look like? So consider the leading term of each polynomial function. What is the end behavior of the graph? And then check your answer with the graphing calculator, because this is stuff that you haven't graphed before. So 4x cubed minus 3x. All I have to look at is this in standard form? Well, there's the highest power right there, and this is the only one after it, so it's in standard form. So that means I look at the fact that this is a 3, and I say, well, that's odd. And the 3 people with phones out right now, you're not doing a really good job of masking that underneath the desk, and I'm just going to come and take those in a little bit. Our leading coefficient is a positive 4. So I think back, odd degree, S-curve. Positive in front, it's going to look like that. So, the limit as x approaches negative infinity of f of x equals the limit as x approaches positive infinity, our graph equals. All I needed was that sketch. I don't necessarily need the whole graph. We're going to plug it in a little bit just to check it out, but we don't necessarily need the whole thing. So, if we're in the center of this graph, and we go to the left forever, we follow that graph as it goes to the left. Are we going up or are we going down? We're going down. Left. So that'll be negative infinity. If you start at that same little dot that I have there, and this time you go to the right, are you going up or are you going down? Going up. Now, just to prove it to you, we'll put her in here, and we'll take you. But the end behavior is going to look just like that. Where we would put the arrows is going to look exactly the same. And you don't really need the graphing calculators right now, so those of you that don't have them, you can just peek up there. Do you see how this is just like my little sketch? And up here, this is just like my little sketch. Now, could I have known that these little lumpy bumps in the middle, the turning points, were going to happen? Right there. There's an X after it. So that's going to make that happen. Am I going to know where those are at in the future? We're working our way towards that. We're going to figure out different parts of this graph when we just see, hey, here's the math that I can do with it. So let's just make a nice little sketch of this bugger here. It looks like it's at about -1, +1, dips down about here, and then back up. And we could do better than that. I mean, we could grab the table feature of our calculator and get some actual points. So on a test, if it says graph, don't just slap things up. Use that table feature to get them on. But we could see the points that I have up there now were pretty clear cut. All right. What about B? Well, we check for standard form. 4, 3, 2, 1. There's not a 1 there, but the constant is back there. That's in standard form. So I can tell what I need to about the end behavior just from that term right there. -2x to the 4th. Okay, it's odd, it's even. And it has a negative leading coefficient. Well, when they're even, they're parabolas. And if there's a negative in front of a parabola, it's because it's going down. It'll look like that. Again, I can write my end behavior just with that information. Limit as x approaches negative infinity of x equals limit as x approaches infinity. F of x equals. Where's this graph going as we go to the left forever? Up or down? Down. So we'll do negative infinity. How about as we go to the right forever? Where's it going? Both of them are negative infinity. We're going to put this one in the graphing calculator. Is this one going to have a lot of lumpy bumps, a lot of turning points? Oh yeah. Look at all those x's behind it. You know, a number back there doesn't make turning points, but x's behind it, this is going to have quite a few. So let's take a peek at negative 2x to the fourth plus 8x to the third minus 8x squared plus 2. There's our lumpy bumps, our turning points up there. But do you see how it's still down and down? I mean, you can see that's negative infinity and negative infinity. And then we could use the table feature if we want to and get some nice points to put in here. Negative 1, negative 16 just tells us we're going down really, really fast. But 0, 2, that would be a good point to use. 1, 0, 2, 2. And then we can see that already going down really, really fast. So what we want to do is make this look like it's almost straight up and down. And we don't want to make any V's out of this because there are no V's. These are for absolute value. We want to make sure this looks like a nice smooth curve. A nice curve. But we didn't need to see that to tell them that. I mean, all we had to know was, is this an even or an odd degree? Does it have a positive leading coefficient or does it have a negative leading coefficient? That's all we had to know. So down here it says consider the leading term of negative 4xy equals negative 4x cubed plus 2x squared plus 7. What's the end behavior of the graph? We don't need that. We don't need it. We need to be able to find the first term. Negative 4x cubed. Parabolic or S-curve? Do you get parabolas with odd degrees or do you get S-curves? S-curves. All right. Is this a normal S-curve or is it backwards? Backwards. Leading coefficient is negative. So it's going that way. Now we can write our end behavior. Limit as x approaches negative infinity, f of x equals, limit as x approaches infinity, f of x equals. Think of an imaginary little dot right there in the middle. As our graph starts there and goes to the left forever, is that infinity or is that negative infinity? Infinity. Start in the middle. Go to the right forever. Where are we going? Negative infinity. It's like a little roller coaster. That's all there is to it. It's not like I told you. It's we start off on Friday and say, oh my gosh, I'm not going to be able to do that. There's got to be like 8 gazillion different types of things that you could graph. Yes and no. I mean, the end behavior just comes from that leading coefficient in that first term, that degree. That's it. So it isn't a big secret. It's not. And we do use our graphing calculators to graph these. So we're not asking you to make a table with 20 different numbers in it. You know, we're saying use the graphing calculator to get that piece. So now what? Well, we need more. I mean, end behavior is great, and that will answer quite a few questions for us, but what about those lumpy bumps in the middle? How are we going to know those? Those are called turning points. Well, that'll help a lot, yes. Tables will help a lot. In general, the graph of a polynomial function of degree n, where n is greater than or equal to 1, has at most n minus 1 turning points. And you can look at all those x's behind it and get a feel for how it's got to work. So if I have a degree 4 polynomial, they're saying it's possible I could have 4 minus 1 or 3 turning points. But it's also possible there's only going to be 1. Here's why. Turning points for even degrees always come in odd numbers. You get 3, you get 1, those are the choices. If I have a degree 5 polynomial, I can take 5 minus 1, there could be 4 turning points, but there also could be 2. And there could be 0. Wait a minute. How can there be 0 turning points? I mean, if it's an odd degree, isn't that an S-like curve? Well, let me make one for you right here. Doesn't have any turning points. It's just a nice smooth curve. It never says, hey, I was going up and now I'm going to change direction and I'm going to go down. It doesn't happen. So if there isn't anything behind it, it is possible that we could have 0 turning points when we're talking about these. But your book is going to ask you for how many at the most. All you have to do is take the degree and subtract 1. That's all you have to do. And then you'll know how many. The graph of a polynomial function of odd degree will always have an even number of turning points. Odd degree, even number of turning points. The graph of a polynomial function of even degree has an odd number of turning points. Yep. Go back and use your odds. That way you'll know, hey, did I put something in wrong? Because this doesn't have all the stuff that I think this is supposed to have. And this gives us a good look at, some examples of where this has happened. This is x to the first. 1 minus 1 is 0. You don't get any turning points. It's a line. Why is it going to be a curve? It's going to be a line. Degree 2, this is our parabola, quadratics. 2 minus 1 is 1. We have 1 turning point with the parabola. It was going down, but then it switched gears and it went up. That's a turning point. Over here, this one, there's never a spot where I'm going up and then clearly I'm going down. So there is going to be no turning point for that one. But over here, going up, switch gears, go down for a while, and then go up again. So 2 turning points for that one. Again, the graphic calculator does show us those. And that's one of those things, unfortunately, we have to use the graphing calculator all the way up through pre-calc because you can't get this algebra to tell you where these spots are until you learn calculus. So graphing calculator is going to help with that. All right, next up we are graphing cubic functions. So we are going to use the graphing calculator. You know what? Limit as x approaches negative infinity, f of x equals, limit as x approaches infinity, f of x equals, and I look at it and well, it's degree 3, pretty obviously it's going to be an S curve, but there's no negative in front of it, so it's going to be a normal looking snake-like curve. Like that. Now, in fact, I know this is going to be really close to this, and how I know that is there's no more x's behind it. There's no more x's behind it. It's just going to be a really nice, smooth curve. No turning points. But let's keep going. So here you are right in the middle of that graph. As you go to the left forever, are you going to infinity or negative infinity? Negative infinity. Boom. Start at that same green point, but this time go right. You going to a positive infinity or negative infinity? Infinity. Going up. And at this point, we would tell you, just grab it back there. And if it's on the test and it said graph, at least write down enough points so that we know what you saw when you punched it in. So, my T-calculator, I know that you like parentheses for fractions, so I'm going to put parentheses, 1 divided by 2 parentheses, x, caret symbol, and that one is right above the division symbol on your calculator, third. Now some of you have the new ones that pop up right away and leave you a little box to put the power in. Now that's nice, however, if you have to type something behind it, you have to hit the right arrow to get it out of the box. So it's kind of messy. All right, Zoom 6. Didn't have any X's behind it. It's nice and smooth. So we go to our table, second graph, and we're going to write down a few of these. So maybe I write down -2, -4, -1, -1/2, 0, 0, 1, 1/2, 2, 4. And the other numbers that I see up there for -3 and +3, they tell me this is going down really fast and it's going up really fast. So I have to make it look like it's almost straight up and down at those points. So let me slide this up a little bit. -2, 1, 2, 3, 4, -1, -1/2, 0, 0, 1, 1/2, and 1, 2, 3, 4. And again, don't forget for your arrows, you need to make it look like it's almost going straight up and down. Can you get that? You're not getting it.
No, I'm getting air.
Uh-oh.
I don't know.
Oh, your snap plots are turned on. See that little thingy right there? You need to get that turned on. Your little stats somehow. A long time ago. Something's not happening?
I've aired in. It's just not.
That's like this. Okay, something is messing with your table settings. All right, yours is probably doing the same thing. Okay, so, see if I can really fix up. That usually means there's something down there that you can't see that somebody messed up. See that. There you go. Somebody's playing. Zoom 6 is good. Anybody else having issues with their graphing calculator at this point? All right. Let's go to the next one. Take a look at B. That's not right. Exactly. It's not standard form. So we're going to have to switch those two around and make that -x³ plus 3x. Is that parabola or is that S-curve? It is S-curve. And there's no negative in, well, there is a negative in front of this one. There wasn't a negative for this one, so we've got to flip this one around backwards to do that little negative piece. So now we write the limit as x approaches -infinity, f of x equals something. Limit x approaches infinity. F of x equals. Everybody all right? Put a big dot in the middle of your S-curve. Now follow it to the left forever. Where's it going? Up. Big dot. Meow. Went up. Go back to your big dot. Go to the right forever. Infinity or negative infinity? Negative infinity. Meow. There it is. Is it possible this one's going to have some turning points? Yes, it is. Lucas? All right, so it's possible this one's gonna have some lumpy bump in the middle. Let's go ahead and graph it, let's see. No lumpy bump? Goes pretty smooth? It's got lumpy bumps.
It's because then if there's negative x.
Oh, okay. Well, let's use that table to get a decent graph of this little puppy. Let's see, negative 2, 2 looks good. Negative 1, negative 2, 0, 0, 1, 2, and 2, negative 2. But the 3's and the negative 3's are showing us, yeah, going up and down real fast again. Real fast. Uh-oh.
Oh.
Yes.
Goodness.
1, 2.
Oh, anybody else having issues with GC? Looking about like so. Anybody else need help? Well, then let's go on. We have 2 more. What is the graph of each cubic function, it says? And again, we're going to talk about that end behavior. We're going to do that first to make sure. Yeah, some of you knew right away, hey, I punched something in wrong because this isn't doing what it's supposed to do. So, look at A. Is it in standard form? Okay, so what degree is it? It is a cubic. So the degree is 3, that's odd. What do you know about the leading coefficient? Negative. Normal S-curve or flipped? It's flipped because of the negative. So instead of going this way, it's going to go this way. So we can do the end behavior already. Limit as x approaches negative infinity, f of x goes somewhere. Limit x approaches infinity, f of x somewhere. And our job is the somewhere. It's either positive infinity or negative infinity. And like I said before, just put yourself a big dot smack dab in the middle. Follow it to the left. Infinity or negative infinity? Infinity. Going up. Go back to your dot. Go to the right forever. Infinity or negative infinity? Negative infinity. Can we expect some lumpy bumps from this one? Oh yeah. There's a following of x's all over the place there. So negative x to the third plus 2x squared minus x minus 2. And I'm just going to hit graph because we've been doing Zoom 6 for all of these. Yeah, we got some lumpies in there. You know, it's a little smoother than the last one, but there's some lumps. So second graph, let's get some table numbers down here. Now I would actually write down negative 216 for this one, and that's because I need something to aim at, you know. Negative 1, 2, that's obviously a part of this graph. 0, negative 2, that's going to work. 1, negative 2, 2, negative 4, but again, I might write down 3, negative 14 just to remind myself, oh wait, this is going down super fast after that. Let me get those pieces. So negative 1, 2. 0, -2, 1, -2, 2, -4. And remember, going up really fast on the left, going down really fast on the right. So sometimes I'll do those first, just so I don't forget. And then the rest of it, a smooth curve. Now, this one we might want to just hit graph one more time to realize there's just a little dip right in there at 0, -2. Comes up just a little bit. And then heads back down. So we can get all that on there. Not so awful with the graph and calculator. But again, we have to know this is what I should see when I punch this in. All right, let's see here. Y equals x cubed minus 1. What's the degree of that one? 3. Parabola or S-curve? S-curve. Normal one or flipped? Normal. Positive leading coefficient. Here's our normal S-curve. So, limit as x approaches -infinity, f of x is doing something. Limit as x approaches positive infinity, f of x is doing something. And our job is the something. Put your dot in the middle. As you go to the left, you going up or you going down? Down, -infinity. Back to that dot. But this time go to the right. You going up or down? Up, infinity. Lumpy bumps. No. This doesn't have an x. It doesn't have an x. It's just -1. That means you move it down 1. So you take the normal graph of x cubed and you just move it down 1. It's going to go through there. It used to go through 0, 0, but now it's down 1. So I have even a little bit more that I know about this graph before I get started. X to the third minus 1. Ta-da! Second table. -2, -9, -1, -2, 0, -1, 1, 0, 2, 7. All of those will fit really nicely. Are we almost out of time? Is that why everybody's... Yeah. All right, so was there anything we didn't get to? We got to it all. Come on, take a picture, otherwise it'll be under completed notes. And I did record today, so it will be at the end of the video.